Welcome to the Frontiers of Physics lecture series, Spring Edition 2026. My name is Marilena Laverty. I'm a professor in the physics department and the chair of this committee, and we're delighted to have you all here to share the latest discoveries in physics. If you are interested in attending future lectures, please sign up for our mailing list and stay involved. These lectures are made possible by the tremendous support of our community and showing up for them. I'm now going to introduce my colleague, Charlie Marcus, who is going to tell us a bit about our speaker tonight, who we're thrilled to hear from.
She meant that it's tonight's speaker that we're thrilled to hear from. She didn't mean it was Charlie Marcus we were thrilled to hear from. My name is Charlie Marcus. I'm a professor in physics department and also the Boeing Johnson Chair in Materials Science and Engineering at the University of Washington. My research is in a field of superconductors and semiconductors and quantum devices, not unlike tonight's speaker. The Frontiers of Physics lecture series started in 2016, allowing us to bring scientists that have made some of the greatest discoveries of our times to Seattle to share with us history, context, and excitement about their work. These speakers have included the famous and pre-famous, from astrophysics to nanoscience, all who share one feature: a passion for discovery and for disseminating those discoveries to others, which is an essential part of science. This lecture series is made possible by the vision and generosity of Dr. Patrick O'Hara and Professor David Kaplan, and comes together with the work of a diverse group of faculty and community members, led by Marlena, who has done this for the last several years. Thank you. Tonight's speaker is John Martinis. John is an experimental physicist whose work has been central to the development of superconducting circuits and their transformation into a leading platform for quantum computing. He received both his undergraduate degree and his PhD in physics from the University of California at Berkeley, and completed his doctorate in 1987 under the supervision of John Clark. His early work focused on quantum noise and dissipation in superconducting devices, work that he'll tell us about tonight, and an issue that would prove fundamental to his later discoveries and realization of quantum coherent circuits and devices. Following his PhD, John joined the National Institutes of Standards and Technology, NIST, in Boulder, Colorado, where he developed precision measurement techniques for superconducting electronics. He later moved to the University of California, Santa Barbara, where his group developed precise control over multi-qubit systems. These advances established the superconducting circuits as an excellent platform for quantum information processing. In 2014, Martinis joined Google Quantum AI as a chief scientist for quantum hardware, where he led the development of large-scale superconducting quantum processors, and under his leadership, the team built the famous Sycamore processor and carried out the 2019 experiments demonstrating so-called quantum supremacy, a computation beyond the reach of classical machines. Then in 2022, John co-founded a wholly new startup, Qolab, which he will also tell us about tonight, where he serves as Chief Technology Officer. The company focused on scaling superconducting electronics toward utility-scale machines in collaboration with semiconductor partners. So, especially to those in the audience who are in the early years of their career and who are thinking for themselves about which path to take, note that John has worked as a professor in a university. He's worked as a scientist at a national laboratory, he's worked at a hyperscaler company, and he's worked at a startup. So if you're having trouble making up your mind, don't worry. There's a path to success, even if you never make up your mind. You know, I have a long list, and it's getting late, of awards that John has won over the years. I'm going to skip the top few. In 2025, John was awarded the Nobel Prize in Physics. Suffice it to say that the parts that I'm not reading above in the text validate that this was not a one-off experience and that he has been widely recognized throughout the community. The Nobel Prize in Physics in 2025 was jointly awarded to John Clark and Michel Devoret for their discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. Across his career, John has played a defining role in turning superconducting circuits from laboratory experiments into quantum devices and systems, and in advancing quantum computing from a scientific concept into an emerging technology. Following the lecture, there will be a brief question and answer period. Please save your questions for then, and do have them ready, because John would love to stick around and answer your questions. I've watched him over the last couple of days, and he lights up, especially when young people ask questions. So please be ready with those questions. We can ask you, if you don't mind, to refrain from recording this lecture. And now, please, let's welcome John Martinis to the stage.
Thank you. That was a very kind invitation, I'm really excited about talking to you today, which is basically my thesis experiment, my PhD thesis experiment. And this is what was awarded the Nobel Prize for, although it's the subsequent developments that really made this important for the field of physics. This work was done with John Clark, who was my advisor, and also Michel Devoret, who was the postdoc at the time, who were the most amazing mentors you could possibly have that really made a big impact on my career. And because of that, I've tried to make this general talk with a few slides kind of geared towards the students, maybe a little bit technical, but I want to give the students a little bit of mentoring and tips, what I received when I was a student, and hopefully that'll help you for the career. Now, I'm going to talk today about what I did for the PhD thesis in 1985, which was awarded the Nobel Prize. I'm going to talk a little bit how the field developed over the next few years. We're really trying to understand how to do quantum mechanics on electronic devices in a really unique way. And then over that time, it developed into the whole story of quantum bits, how to build a quantum computer, and I'll go through the history talking about the quantum supremacy experiment that was done at Google. And then at the end, I'm going to talk about what I'm doing right now, starting this company, Qolab, and focusing, we have to make better qubits, really how to manufacture the qubits so they can really scale this up in the way that we want to. Now, for our thesis, my thesis experiment, it basically answered the question, do macroscopic variables obey quantum mechanics? This is the first mentoring for the students here. When you write your paper for doing an experiment, you're often thinking you're going to start the paper with, recently there has been much interest in blah, blah, blah. Do people understand why that's such a horrible first sentence? Because you're not doing science just because everyone else is doing and you're following the crowd. That's not who physicists are. You're doing it because you want to ask nature questions about how it works. You want to answer questions. And we were very fortunate in this experiment to ask a very simple and basic question and have a concrete answer for it. Now, I'm going to have to explain, first of all, what macroscopic variable means and the like, but let me first motivate why we were interested in this question. It was actually motivated by Professor Anthony Leggett, who passed away about a month ago, a little bit more than a month ago, who was thinking about the famous Schrödinger cat experiment. Oh, and by the way, for those of you who are interested in quantum biology, this is the closest I'm going to get to quantum biology in the whole talk. And I'm sorry, I apologize for that. Okay. So the idea in the Schrödinger cat is you have some microscopic system, an atom that decays, And if it decays, it opens a bottle of cyanide and kills the cat. And you have it in this box. And according to quantum mechanics, kind of, is if you don't open the box, you haven't measured it yet, and the cat is in a dead plus alive state, and then you open it and you find out which it is. And it's kind of weird to think about this big object, especially in a living object, is obeying quantum mechanics. And what Leggett did was something very interesting here. He said, well, you know, there's actually no evidence at all, no experiment that shows that a macroscopic object could obey quantum mechanics, and we should be testing to see if there's any system at all that can do so. And it turns out he understood that these Josephson junction systems could be that, and that you could actually do the experiment. So he really set up everything for us. Now, just for the physicists in the audience, but this is kind of interesting too, it's possible to see quantum mechanics, which is normally you think of the physics of the microscopic, like atoms and photons, electrons, whatever. You can actually see quantum mechanics observable on the macroscopic scale. This is a different phenomenon. You can talk about flux quantization for the physicists, but for the general audience, think about looking at a crystal. And I have a picture of a quartz crystal here. In that, looking at that macroscopic object, you actually know how the atoms are stacked up in that crystal. They are bonded together in a certain way because of the way quantum mechanics work. But then since it's a regular stacking up, it keeps on stacking up on larger and larger scales. And you can see, you can see that. And the orientations of the atoms are displayed in this. This is not what we're doing. Oh, I wanted to mention, this example of crystals is actually a very important economic value in California and maybe in Washington, I have a feeling. And that's because crystals have this very magical healing power that I think you all know about, okay. They're useful for things like semiconductors and silicon too, but you know, this is not the macroscopic we're talking about. We're talking about here, take a macroscopic object like a ball and throw it against the wall and it bounce off, but there's a finite chance quantum mechanically that will go through, it'll tunnel through the ball. It's normally very tiny, but if you set up the experiment right, then you will be able to see that, and that's what we're going to talk about. Now, just to talk about a macroscopic variable, again, this is a little technical, but I want to explain what's going on here. You can think of a macroscopic variable, you take some lump of some matter, and you heat it up enough, it turns into a gas, and the atoms are flying all around, and it's a very complicated. You have to know what the atoms are doing as they're flying around here. Very complicated state to know exactly what's going on. But if you cool it down so that it condenses into a solid, then all the atoms are rigidly held next to each other. And now if you just talk about the center of it, maybe the angular coordinates, just a small number of coordinates, you now know exactly what's going on in the system. And we call that a macroscopic variable, this like center of mass here. And that's what we're looking for tunneling. Now, the same thing happens with electrons in a metal. At high temperature, you know, copper or whatever, the electrons are a little bit complicated with something called a Fermi statistics, but the electrons are basically flying around, doing their own thing, very complicated. But when you cool them down into a superconductor, these electrons pair up. And electron going in one direction pairs up with electron going in exactly the opposite direction for all the electrons. And then there's a free degree of freedom in this. This is analogous to the center of mass here that then describes the state of that superconductor. And if that phase state has a change from one position to the other, that corresponds to current flowing to the superconductor. And this is a current that has no decay, no dissipation. And it's, for example, when you get into the MRI magnet, there's a huge currents flowing around the magnet that doesn't decay because of this superconducting state. It's really very useful. So because all these electron pairs have the same phase, it adds up to a large current, like you have in the MRI magnet. Now, although you have this current flowing through there, you can't put an infinite amount of current through that wire. At some point, you put too much current, and it kind of breaks the superconductivity, and that's the physics we're going to be looking at. In this particular case, what we have is aluminum metal that's separated by a very thin aluminum oxide, and that's thin enough so that these Cooper pairs can microscopically tunnel through this, and it gives us a current that's proportional to some number having to do with the thickness and the size of this, times now it's a sign of this phase difference, it's a sign of the difference. And you see here that there's only a maximum amount of current that can flow through this according to that equation. And what we're going to do is look at the physics as I gets very close to I0, and then have this phase difference here looking like a macroscopic variable that we want to do that. So to understand that a little bit more, okay, again, we have to go into some math to understand this, but this is very generic physics. I hope a lot of people have seen this already. The basic physics is that we're looking at a current, 0 voltage, and then at some point, if you put too much current into it, it goes to the voltage state. Now, when I is less than I0, you're at 0 voltage, and what happens is this is thought about as a marble, a particle, moving in a tilted washboard potential. And this marble might actually be oscillating around in there and jiggling around with thermal noise, but if it's sitting here, it has 0 velocity, 0 voltage, it's in a superconducting case. As soon as this goes over this nearby well, it starts rolling down this, and then that corresponds to a voltage state. So we're looking, the physics here is what happens as the current gets very close to the critical current with this kind of escape mechanism. And the nice thing about this is very typical of many physical systems, certainly chemical systems, where it's the escape of a potential barrier, where you have this potential barrier, delta U, and the escape rate is kind of given by the attempt frequency times an Arrhenius factor, exponent of delta U over KT, or a Boltzmann factor, as physicists talk about it. And you see as delta U goes to 0, I goes to I0, this goes to 0, then this can be very large, okay? And then also in the quantum mechanical regime, this is what we're interested in. Does this obey quantum mechanics? You go from a thermal formula to a quantum formula given by this, where now KT is replaced by an energy h bar megaplasma, and there's this 7.2 here. And that kind of describes how this can go through the tunnel here. Notice also we're going to know in the future that even though as I goes to I0, delta U is getting smaller, the frequency here is also getting smaller, but with a much slower rate because of the 1/4 power law. So these are the basic controls here. Now let me, I often got asked by the journalists after the Nobel Prize, what is this quantum tunneling and the like? And I started out saying, well, there's this wave function and it leaks under the well, and no one understood that. So I'll use an analogy here, which actually is not so bad. And the analogy is quantum mechanics is like a really risk-averse banker, a nervous banker, okay? And nature as a banker can give you delta U to go over the well, but it can only give it to you for a short time, t, so that this time it gives you, where it recalls the loan, okay, delta U in the recall of the loan time is given by h bar 10 to the minus 34. It's a really small number. And what you need to do is make sure that this is a really high frequency so that the characteristic time t, which is 1 over that, can be small enough in order for it to do, and delta U has to be small enough. So that's the way to think about it. Now, the one nice thing about this is, again, this is getting into deeper physics, but one of the new things that was understood in this is when you build these macroscopic systems, it's not like, electrons in some perfect atom system. It's connected to wires and the rest of the world. And you can have energy loss, you can have dissipation in the system. And you want to know what's the effect of dissipation on it. And it turns out that if Q is, 1 over Q is the dissipation, Q is how many oscillations it takes before it loses its energy in here. And what happens is, if you have loss, this number gets big, and then the quantum tunneling rate gets smaller and smaller. And it's in the exponent. It's a big effect. And you can understand this with the banker analogy in the sense that because it's losing energy, if it wants to go from here to here and borrow this energy, go here, this movement is going to cause it to lose some energy. So it has to borrow a little bit more delta U in order to, converse this, and that makes this a smaller rate in the exponent. It makes a big effect. So I think that's a good way to think about the physics of this. So now, again, I want to talk about the experiment, and this is, again, for the students here. So we got all excited. We were going to do the experiment. We hooked it up in some very simple way. This is kind of the way we were always doing. We're testing it at 1 Kelvin. It's very easy. And the results were a complete disaster. Didn't work at all, didn't make any sense, wondered what was going on. And because of that, we had to kind of retrench and say, okay, how do we really understand this and get it to work properly? And this is an incredibly important thing to do when you do your experiment, because initially you may not have all the ideas right. And there were 2 main ideas we had to think about. One is that this is a very sensitive device, and we have to filter out all the noise that's coming from, room temperature and others. So we had to filter that really well. And we filter that with something with a copper powder filter, because copper powder is very strongly dissipated. It dissipates at all frequencies. It absorbs the energy instead of reflect it. We talked about this yesterday, okay? We reminded everyone about this. Is really important. And then the other thing is that you had to do a microwave engineering of this. So you have this chip right here. It's about 1 centimeter across. You see it right here. This is the cross where we have the Josephson junction. And then it looks into what is essentially a coax cable of your line, which you see, connected at least to your older TVs. And that forms a very well-defined microwave circuit for us. So we had to design that properly. We have this microwave connector, which is here, that injects microwaves into the qubit so that we can push it and force it and do interesting things, which we'll talk about. And it was really after we did this and designed it. I'm very proud of this picture because I machined that myself, okay? And after we did this and we cooled it down and did it, everything started working perfectly. We understood what was going on. So we really had to work hard to figure out what the physics was. Now this is the next thing for the students that I want to emphasize is when we thought about this, previous experiments were kind of murky in the sense that they measured something, they just measured some effect versus temperature. At some small temperature, it stopped changing. Well, then it's quantum tunneling. Well, you don't know that. What we did is we decided we have to measure all the parameters carefully so that we can compare the experiment results we got with a theory, which I just described. So that's kind of why I introduced the theory. And it's very important to think carefully about how to measure this. So there's 2 parameters we basically have to measure. One is this oscillation frequency. It's in this well. It's oscillating at a microwave frequency. What's that frequency? And the second is what's the barrier height. Those 2 things we need to measure. So how do we measure that? Well, first of all is we ramp up the current, and it escapes the voltage state a little bit before the critical current. And we measure that switching at some rate, which is our base rate that it's escaping. And then we put in microwaves at a fixed frequency, and we watch that the rate goes up, because what you're doing is you're resonantly giving energy to that particle, giving it more energy, and then it can escape faster. And if you set everything's upright In this case, we were driving at about 5 gigahertz in a thermal regime, 151 millikelvin. You saw nothing much happen down here, but then here, the escape rate went up a significant amount and then came down here. And where it's maximum here is where their drive frequency of the microwaves equals to the natural oscillation frequency, so we can tag that as 4.9 gigahertz. And for those of the physicists looking at the slope right here can tell you the width and tell you something about the damping. So we can get all those parameters that we need. Okay, that that all works fine. The next thing is how to measure this barrier height here. So we're changing this bias current, and we're measuring some escape rate versus the bias current. But we need to plot it in the right way. So this is probably the most important thing for the students to understand here. And when I read papers, people, experienced scientists, no longer obey this rule. And my job as a Nobel Prize winner is to get people to start plotting their data on the right way, which is the way we used to do it in the old timer when we didn't have computers. You went to the store and you bought graph paper that was log, linear, whatever. You bought graph paper. And what you want to do, this is the secret. You want to plot your data so that it falls on a line. Okay, why? Why would you do that? Because you take your piece of paper with the plot on it, okay, and then you turn it and you look, okay, is it a line or is it curved or something? Because you really want to understand if it's obeying theory in some sensible way, okay? Now, you know whenever you're plotting Arrhenius laws, I hope when you're in your chemistry physics class, you usually plot on a log scale here and a linear scale here, and then you get some rate, okay? There's a log linear. So we kind of do that here, but here it's this funny unit where we take the plasma frequency, which we know, and we normalize that to the escape rate that we measure, and then take the log of that and then go to the 2/3 power. And you say, well, why the 2/3 power? Remember, the barrier height went as I minus I0 to the 3/2 power. So it kind of undoes that 3/2 power. And then when you measure, let's say the data here at 400 millikelvin, this is the data, and you see, you plot it this way, and it goes in a very, very nice line here. And again, you can look at that carefully and make sure it's really good. And then the added bonus is that you can extrapolate this line back to here, and this is where delta U is going to 0, and that's where I is equal to I0. So this tells you the critical current. And then you can do that at other temperatures, and again, you make sure it's on a line, and make sure everything's okay, and then you go lower and lower, it gets steeper and steeper, and then from around 30 millikelvin or so, it stops changing. And that's where you think, okay, I'm starting to see quantum tunneling because it's not changing anymore, okay? But that doesn't prove it, okay? That's just, oh, that's exciting, that looks good, and the like. And you see all these lines basically extrapolate to a common, it's not like this I0 is going in, and this little difference here we understand, it's due to prefactors, so that's okay. So straight line is a check, and the slope gives us the escape tip physics. If it's at a high temperature, it's a low slope, and a low temperature, because the Arrhenius law goes as 1 over delta U over KT. Okay, so this is great. You can then get all the parameters here. Now, from this, the slope of this line, it basically can tell you what the effective temperature of the qubit was, which we call the escape temperature. You can extract that from the data. It is as if the qubit is that. So by measuring delta U, knowing the omega plasma, knowing gamma, we can get a T escape. So this is the escape temperature, and here's the real temperature in a dilution refrigerator from about 20 millikelvin to 1 Kelvin. So this is all good low temperature physics. High temperature, T equals T escape, exactly as you expect. and then it levels out right here, okay? So that looks like tunneling, okay? But you're not done yet. You have to compare it to the theoretical predictions, and that's what this little bar here is. We plug in all these parameters, and with uncertainties, this agrees here, okay? Now, we were really paranoid, and we wanted to say, is there even a better way to check that? And there is a better way to check that. And what we can do here is we can put on a little, this right here goes to a little coil of wire, and we put a magnetic field here, and that will effectively decrease the critical current by about a factor of 5. And when you do that, you lower the frequency, and thus it's going to behave less quantum and more classical. And this is classical junction with the lower critical current, T escape equal T, and then it rounds out at a lower temperature, you know, as you expect. So that's a really good check that, for example, there's no noise getting into your system that's causing it to level off. It's, you know, it's really the physics that's doing that. So, you know, we did a lot of checks to make sure that this was working right. And I would say it's great because we just got into the mode of really trying to do the experiment well and to check it as best we could. Okay, now I want to talk about the next experiment we did to prove quantum mechanical behavior another way and point towards the future. And this is seeing energy levels in this system. And quanta in quantum mechanics kind of goes to the idea that you see energy levels. So let me explain this first with an analogy or experiment I did at NIST with Sewunam in 1998, demonstrating something. When you look at an incandescent light bulb, I hope they still are some around, but that's just a piece of tungsten wire. You run current through it, it gets hot, and it radiates light of all different frequencies, so it looks white, okay? However, if you were to take neon gas and run current through a neon gas, we all know you get very distinct, vivid colors. It's not white anymore. So why is that doing that with neon gas? And that's because neon is an atom, it's a quantum particle. And the way that the electrons move in there is only moves at kind of certain frequencies. So if you excite it, you excite certain frequencies of the motion, and then it gives light out at that frequency. And it's this quantum mechanics of this quantized light that really was strange in the early 1900s and had to be kind of figured out. Now, what I want to do here is talk about the modern version of Planck's law. So for the new students out there, at some point you'll learn about Planck's law, which is where H bar or H first came into existence to explain the data of black body radiation. You heat up something and you get radiation coming out of it. It's what happens in a light bulb. This is a very complicated calculation when you're a new student, because you first have to assume this quantum mechanics, which is kind of strange, quantized energy levels, and then you have to go through all the statistical physics, which is, you know, very conventional. You do it many times in your career, but it makes it very complicated. What I believe is the textbooks should be showing another experiment where you can directly see this quantum mechanical behavior. It's kind of amazing. And it's only because of new quantum devices that people have been building in the last 30 years that it's so simple. So it's a very simple experiment. You take a laser, let's say at room temperature, and you pulse it for a few nanoseconds, and you bring some energy coming down your fiber optic light. And then there's some attenuators and the like, and you shine that on to an energy detector we called a microcalorimeter. And that energy detector absorbs the light, and being a microcalorimeter, that energy gets converted into heat, and it heats up, and then over time it decays back down to whatever base temperature it's at. And the heat that it rises to is proportional to the energy that it got absorbed. Very simple, okay? Now, When you do this, you expect that the temperature rise to go up and then to go down, and the brighter the light, the higher it is and the like. When you get into the quantum regime, this is what you see. You see this going up and down, but there's now bands of where the temperature goes up. And if you histogram the peak height here and look at thousands of events, you see the ground noise, and there's a peak. Here we label 1, and then a second peak 2, and a second peak 3, and 4, and 5. So instead of this being one line, it's a series of lines that are in fact separated by Planck's constant times F. And this is the point of the Planck radiation. It's the assumption of the Planck radiation law that the energy, when you measure the energy of a light pulse, it comes in quanta. And this is, the really surprising things about quantum mechanics is that light would behave that way. So you can directly see this. You don't have to go through any statistical mechanics. This is actually a Poisson distribution, so you can understand that. But it's a really direct emphasis. You just see it on the oscilloscope, this strange nature of quantum light. So this is because energy comes in quantum values. Now, this is what we were seeing in the experiment also. And remember, I told you before that we put in, we look at the current and we look at the change in the escape rate. And what we did this for this device with 2 gigahertz, and now we see these 3 peaks, very distinct peaks. And that represents energy level transitions. Here, corresponding to the 0 to 1, here the 1 to 2, and here the 2 to 3. And you can work out what the quantum mechanics says with the uncertainty, and this basically makes sense. So the quantum system only wants to accept being resonated with, being excited at certain frequencies corresponding to the quantum mechanics. Very direct observation of this, and really, we think in a qualitative way, shows that it's working properly and you're seeing quantum mechanics. Now, as we go ahead and talk about qubits and the like, we're going to use these 2 states here and this transition to make quantum bits and to do this. Now, these are very broad transitions. This is not designed in a sophisticated way, but we've been able to make this extremely narrow line in the last 40 years to be able to manipulate these states really, really well. So before I go on, let me just talk a little bit about what we've done here. We're all familiar, physicists, okay, I hope chemists and general public, I hope, that quantum mechanics is the description of the small, generally, how atoms work, how nuclei work, how photons work, how electrons work. And that's been known for a long time and very important technology. And with that, you can put together your atoms and your molecules with the periodic table of the elements. That's your basic building blocks. What we've done here with this new system is we can now build quantum systems with new building blocks of capacitors, inductors, and transmission lines, and Josephson junctions to build these superconducting circuits. But what has been really interesting in the field is people have also included parts like nanomechanics and microwave photonics, nanomagnets, to build these kind of macroscopic atoms. So the playground for physicists to explore, quantum mechanics has increased over time, and we really like having a new playground to play in. So that's great for the physicists. So I'm going to talk next a little bit about what happened after this. Again, it's a little bit technical, but it's kind of interesting what's going on. In this experiment we did immediately after my thesis, I went to France, and what we wanted to do is actually directly measure the time it takes to go from here to here. With my banker analogy, how long is the banker loaning us the energy for? So this is the picture of the more sophisticated. We understood what we were doing now. So this is a circuit board, with a Teflon circuit board where we have copper here and here, and this are grounds, and this is a center line. in how we junction. So this is all tapered now and made better. And then we have a load here, which capacitively shorts the center conductor to the ends. And this is such that if you look at the traveling impedance, the wave impedance of this line, that's 70 ohms, but then under here, because of the short, it goes to 20 ohms. And what's interesting about this, even though it's very cold, we attached a string to it, and then at the top of the refrigerator, we're able to pull on the string and change the distance from here to here. Now, what happens is when you change the distance from here to here, at high temperature, the escape rate, the escape time, whatever the escape rate, changes very little because it's just only having to do with that Boltzmann-Arrhenius factor. So that's really flat. However, if you remember, I said that the damping affects it in the exponent, so it makes a big effect. So you go to very low temperatures, and now with the data, you see that it makes a large effect here by about a factor of 4. And what happens is when it's short here, the junction is looking to a low resistance here. There's a lot of damping, and then the time goes up a lot. And then when it goes at a far distance, it's looking into the 72 ohms, low resistance, and it's a much lower. So kind of the two ends make sense. But what's interesting is the curve between here and here and the characteristic time. This is the energy borrowing time, the tunneling time, which is about 2 times 30 picoseconds. And what's happening here is that as you increase the time delay here, it goes to this because when this tries to borrow its energy, it borrows the energy, but the fluctuation it takes going over the well, by the time it goes down and sees the end of the line and comes back and interferes with itself in a quantum mechanical way, it's already tunneled. So that means the end doesn't matter anymore. So this kind of tells you the characteristic time at which it tunnels. And it's a really nice way to measure this very unusual but fundamental property of quantum tunneling. This is still argued about in the field, what this time is. Okay, so now what we're going to do is transition to the qubit era, and let me explain a few minutes why we're interested in quantum bits. And that's because of the quantum mechanics. Storing information into a quantum state allows you to do much more powerful processing. Now, you know when you do classical processing on your phone, okay, you know that that's stored as bits of 0 to 1, and you string together a bunch of bits to make words, and then you process that. In quantum mechanics, you can actually store the information not as 0 plus 1, but as more complex quantum states. For example, something that we call in quantum mechanics as 0 plus 1. And what happens in a quantum computer is we have all the old operations we had in a classical computer, but we have new operations, an expanded instruction set, such as taking a 0 state into a 0 plus 1 state, this really weird quantum mechanical state, which I'm going to say is a square root of NOT gate, which you don't have classically. And then you can use this square root of NOT gate to build new algorithms and do very powerful processing. So quantum mechanics gives you this extra power. So what happens with this 0 and plus 1 state that we create here? You can imagine taking 0 plus 1 and then running it through your quantum computer, and then going through the quantum computer, you're measuring, you're computing what happened with the 0 state when it went through, and what happened to the 1 state when it went through. And that is some kind of parallel processing where you're now doing 2 possibilities running through the computation, but only doing it once. So you get kind of like a parallel processing of a factor of 2. Okay, big deal, right? So physicists, that's new, but it's a big deal. But what's really interesting is if you start doing this with more and more qubits, so for example, 2 qubits, you now have 4 states that you parallel process through. And with 3 qubits, it's going to be 8 states, 416, 532. The amount of parallel processing in this kind of way is growing exponentially with the number of qubits. So by the time you get to 50 or so, 2 to the 50 taxes a supercomputer, and we'll talk about that. Whereas by the time you get to 300, which we're not there yet to do it properly, 2 to the 300 is more states than there are atoms in the universe. So this is a huge amount of processing. Okay. Now, there's a problem here in that although you get this parallelization going on, at the end you still have to measure it. And when you measure it, you just get 50 or 300 classical bits of information. And you can't necessarily look at it. It collapses the information. So you have to build very special algorithms so that even though you're getting a minimal amount of energy at states at the end, you can then figure out something about your algorithm. It means that there's only certain algorithms work. You can't do that for any classical computation, but there's still some things you can do with it that are very powerful. So just talking about the algorithms very briefly, okay, the first thing you can do with a quantum computer is you can break the internet, or more importantly, sooner term, you can break Bitcoin. And there's a lot of money in Bitcoin, okay? And so there's the Shor algorithm, there's quantum resistant protocols. So you're not going to break the internet because they're going to replace all our protocols from the RSA, which can be broken by a quantum computer, maybe 5-10 years, maybe longer, but eventually you can replace that with quantum resistant algorithms. So I don't see there's a problem there. Bitcoin, it turns out, is a little bit easier. And there's some new papers out that are a couple weeks old that if you're interested in Bitcoin security, you really need to read those papers. Okay, they're very interesting, and one has to think about it. I don't want to break anything. I don't want that to be my life's ambition, okay? So what I'm more interested in is quantum chemistry. This is something, in fact, Feynman talked about, and the basic idea is that it's hard to simulate atoms and molecules because they're quantum, okay, for the same reason that it's powerful. And you can map quantum chemistry into a quantum computer and solve it. So there's many technical algorithms. There's some really interesting ideas how to do that. You need to have error correction. You're talking maybe about 100,000 million qubits to do it right. But to me, there's a real opportunity here to build advanced materials and make all our lives better. Let's say finding more ecological materials or having a better supply chain, that doesn't go through the Strait of Hormuz or whatever, Okay. And then there's some optimization and machine learning. This is a little bit more speculation, but there's a lot of interesting things you might be able to do with that too, and that's important. In terms of building the systems, there's a large number of systems. We're talking about superconductors, ions, photons, semiconductors, annealers, neutral atoms. Really interesting and many approaches, a company, startup, government labs, universities. Really interesting time, all these different approaches, and see what's working here. I'm going to skip that and talk about I've been working on this my whole career, trying to build up this quantum computation, and it really culminated when I was working at Google with a bunch of very talented people there with something called the quantum supremacy experiment. And I would like to, ask a question, okay? Does this macroscopic quantum computation, does it still obey quantum mechanics? Does quantum mechanics work on this quantum computation scale? And in particular, this is a 53-qubit device. You can see here, the qubits are the gray crosses. We have adjustable couplers to connect them together. 53 qubits, they're under here. Here's all the wiring on the outside. The qubits are on this chip that are indium bump bonded down to the device. Well, lots of control wires going around here. But at 53 qubits, the amount of computation we're doing is 10 to the 16. It's a macroscopic number. And the basic question we asked was, if we did this, would we see quantum effects? Would it do the quantum computation? Now, we did a very simple computation where we generated random numbers, pseudo-random numbers, but they weren't exactly random. Some numbers were slightly more possible than the others, and then we checked the output we got out of our quantum computer with a quantum simulation, which with 10 to the 16 states was really hard to do. And although our quantum computer chip is not perfect, and no qubit chip is perfect, even though it wasn't perfect, it did work for some fraction of the time. And what we showed is that there were no additional dirt physics, error mechanisms, unknown physics we didn't know that about, beyond what we knew that the 1 and 2 qubits are making their errors. So it really showed that quantum mechanics is operating in the way we would expect. And this is really great. And since then, people have expanded on this, and it's a really good test to see, is my quantum computer working properly? And what we see is that the physics, basic physics, looks good. So it's a really important part of that. So here's 1985, okay? Here's Google by a bunch of really great people working on this together. You can see the big technology jump from here to here in, what was that, 34 years, okay? We had a long way to go to build that. And then my question is, well, what are we going to do in the next, 10 decade or so? What is this thing going to look like? What do we have to do? And what I want to show next is what my vision is of what it's going to look like in the next 10 or 11 years or so. That's what we're working on. So let me just say here, again, for the students, what I'm going to show you is my vision of what this is going to look like. When we show this to the superconducting qubit field, they're very doubtful this will work. Okay, it seems like a big stretch. It's really different than what people are doing now. And it's kind of depressing that people don't get it, but also it very much reminds me of all the important experiments I've ever done in my career that people don't understand it, don't get it, they don't see how it's going to work, including the quantum supremacy experiment. So this is actually a good sign that people are a little bit doubtful here, okay? Although you have to make sure you're not deluding yourself. That's equally important. So why are we doing this? Here's the Google experiment in what I call the golden chandelier, okay, which has the little tiny qubit chip is right there, and then you have all these coax wires and filters and microwave components and all these lines going up to room temperature to your control electronics. This is what people have been doing. All the companies are doing that. And they're working to improve that. But when I look at this, what we're doing right now, is nice. We got a long way with it. But it kind of looks like what a classical computer looked like in the 1950s and 1960s, with some transistors somehow buried in here with tons of wires going around here. And, okay, you got computers to work, and it was useful in starting it up, but it's kind of not what you want to have to look like. What you really want to do is make it look like this. This is a microprocessor in the 70s, where you've put all your transistors and wires on one chip, and you can mass produce that easily and cheaply and well, and then you can do that over and over in the future and build really powerful processors. So this is our vision of what we want to do in a nice way. And it's really just taking advantage of the semiconductor industry. Now, the next thing I want to do is talk a little bit about where the field is now. Again, people don't like me showing this, but I still like to show it anyway. This is the number of qubits. And actually, what's nice about superconducting qubits, as we've made more and more qubits, they've become better and more complex. So this is a proxy for complexity. And we're not just making more qubits for the sake of it, we're making it better, okay? So this was at UCSB, 9 qubits, and then I moved to Google, and with the team, this was 53 qubits, quantum supremacy, which is great. And then I've left since then, but since then they have about 100 qubits and doing really nice surface code experiments. It's 2025 or so. We're right here. Now, in 2019, we were all excited. We said, look, let's build a big, powerful quantum computer, let's say utility scale, solve real problems, error correction, general purpose, about 1 million qubits. So that's what we were talking about here. And look, this was like 20 experimentalists, and now there are hundreds on it. So yeah, okay. Well, what's happened is they've gone from here to here, okay? So that's what we wanted to do. We're here to here. And this really worries me, and I'll explain why. If you extrapolate this out, it's getting better, that's great. But if you extrapolate this out at the current pace and think about your 1 million qubits, I predict I will certainly be dead by the time it happens. And I'm going to say for the students here, I'm thinking about you, you will be retired at best. Okay, that is not good. Okay, we want to accelerate this. How are we going to accelerate this and get much better here? This is what we need to do. And people are working on it, that's for sure. But I want to radically accelerate this. And the way we're going to do the solution is we're going to do qubit fabrication with tool builders, such as Applied Materials. They make the semiconductor fabrication tools that go into like TSMC, where they can build your many billion transistor chips that go into your phone. Okay, they know how to make materials really well. The problem is they know how to make CMOS materials well and not such things superconductors. So we have to work on that. So this is just showing what we're doing is a custom 300 millimeter deposition tool. The wafers are about this big. This is different chambers. So in one vacuum system, you can go between many chambers, not to break vacuum, and do it well. And this is in their R&D prototype clean room facility where they can build that. So we're basically focused on reproducibility, quality, scaling up. We can improve every process step and make this in a way that really will work well for building these qubits in a good way. So it's really exciting to work with these experts. Now that was a very aspirational slide, okay, which is great. I want to show there's actually some meat to this, okay, a little bit for the experts. But first of all, if you look at the process of superconducting qubits, we use something, this 60-year-old plus fabrication called liftoff. You take a wafer, you spin on a stencil of photoresist and expose it, develop it away, and then you evaporate aluminum on top, which forms the structures, and then you stick it in acetone, and then the rest of the aluminum kind of peels up from it and gets washed away, okay? It's very simple, physicists love it, but no one in the CMOS industry does this. I once talked to a TSMC engineer, and he started laughing when I told him we did this, because it's so dirty, you just cannot make advanced devices in a good way this way. So it's very hard to change this. We want to use deposition and etch, and this is an example where we have aluminum base, we put SiO2 everywhere, we make a little hole in it, what's called a via. Semiconductor industry knows how to make vias, they do it all the time. We then clean it off, put aluminum on top, and then remove the silicon dioxide at the end. And we can make devices this way. We have to make them better, but it works. We can do that. But we have to make good devices for it to matter. This is a picture of a silicon wafer, the aluminum on top of that. We have very, very clean interfaces here. And this is actually a single crystal aluminum that's about 10, 20 microns across. It's very beautiful. It's just amazing that Applied Materials can make kind of perfect materials here. And then finally, probably as important as everything else, we want to do wafer scale integration. And I have a slide, I have a slide doing that. There's a company in Silicon Valley called Cerebras, where everyone's making powerful AI processors, and they're making a single AI processor that dissipates about 10 kilowatts on one single 300 millimeter wafer. And they're building AI ABI systems out of this. And this is an example that, well, you can actually build such devices. So we're going to use wafer scale integration, advanced semiconductor macros, and we think this is how to get inexpensive scaling. So the basic idea is here. We build qubits about 14 centimeters by 14 centimeters, about that big on a single wafer. It's about 20,000 qubits. We then take a silicon wafer and connect that from 20 millikelvin to 3 Kelvin with about 100,000 wires going from here to here. And for those of you who know about silicon, you're going to say silicon has the thermal conductivity of copper. You're right. This won't work. You're wrong. There is a way to do this. Okay? And we'll eventually talk about it. We think this is just really the way to do cryostat wiring. And then at 3 Kelvin, we have another wafer where we can put cold CMOS or superconducting electronics, whatever we do. There's a lot of cooling power at 3 Kelvin. We can do that. And then we use flexible circuit boards that connect this to maybe CMOS at 300 Kelvin to do all our control. And again, this is mass-produced, ASICs mass-produced, these things mass-produced, specialized things here again, all using wafer scale integration. This is kind of where the semiconductor industry is going, so we want to do that. And then that's 20,000 qubits, and you can then stack these together, tile these together to make more qubits and the like, okay? So to do all this, it's very complicated. We're focusing in at the low end, making these quantum processor units. And we're doing that as we're kind of the system integrator. We're working with Western Digital Corporation, Applied Materials. We also work with Synopsys in terms of the design software. And then at the high end is Hewlett-Packard Enterprise, who makes supercomputers. And we have a bunch of startups. We have national labs. We have universities we're working with. And if you want to know, what we're proposing and how it's going to work, we have an archive from a couple of years ago, 24, how to build a quantum computer scaling from hundreds of millions of qubits, and we describe this. Okay, we don't give all the good stuff because it's competitive, but we tell you basically what we're going to do. So that's there. And in the end, you have to show a picture. We're going to have a bunch of dilution refrigerators that we're connected to each other for lots of wafers, and then wiring to a bunch of electronics to control and do the error correction and the like. So this is what we're looking at. And again, we're looking at maybe 100 to 200,000 qubits for dilution refrigerator, which is a good density of that. Okay, with that, let me just summarize. That's what we're trying to do here. I'm thinking about the future. I think there are significant hardware and software challenges which are, I think, either minimized right now. I think people are being a little bit optimistic or overlooked by existing efforts. And our idea is to leverage the semiconductor industry who really know how to scale up and to fabricate. We have to totally revamp and redo everything, but we think it's the right way to go. Again, we're doing this with a lot of partners. Qolab stands for quantum collaboration. And we're also hoping that could be eventually a new Scrabble word without the U. So that would be good. And then finally, the cost. We want to scale to millions of qubits with wafer scale integration. And we think this is what's being done right now with these giant GPU systems. And that's the way we think you're going to do this in an efficient way. So we have a lot of work cut out for us, but we're really excited about pushing this technology forward. So thank you very much for your attention.
Now, there's some plans for question and answer. There's a plan. There's a plan for question and answer. Is that working? Yeah. Good. There's a plan for question and answer, and it is that we ask people to come down and use these microphones on the front. If you, for some reason, aren't comfortable coming down to the front, raise your hand, and I'll try to run up with a microphone. But our preference would be if you could walk down with your questions for John, please do so now. Form a line if needed.
Hi, Dr. Martinez. Thanks so much for your talk. It was wonderful. My name's Grace. I wanted to ask, with brand new technology and things that are cutting edge, in the past, big discoveries have really changed the face of how the world works, whether that's nuclear fission or fusion or AI, and the quantum revolution might have the potential to do something like that. So what do you think is the role of physicists or scientists in general who are developing this technology in influencing the direction and applications of that?
Okay. So let me just say an interesting thing. As we try to get companies engaged with us, it's actually a little bit hard because they're just treading water, keeping up with AI, okay? And, you know, they want to make money off the AI, but there are companies who are looking beyond the current AI revolution and thinking about what's next, and then they're interested in quantum because of that. But, you know, the company has to be comfortable enough with what's going on now with AI to be able to do that. What I would say is, if you look, you know, at the various things you talked about, I'm really happy that fusion is getting funded now because there have been some of these ideas. You know, I look at, you know, SpaceX and what's happening with that, you know, in the various ways. And I think it's kind of interesting that there have been some really new things coming out in the last, you know, 10 years, 20 years, something like that, where there's all these exciting technologies to work on. And that wasn't so obvious when I was a student, okay? And things have totally changed, but it just points to the fact that, you know, people are pretty creative in, you know, thinking about new things. And, you know, what's the next new thing? I don't know what that is. I mean, I'm at an age where I just have to focus on, you know, doing what I'm good at. But I think that's very exciting for young people. Because you don't, I had no idea this would turn into a big field when I did my thesis. I thought it was a great experiment, thought it was very fundamental and nice, but it's only because of many other people generating the ideas for a quantum computer that this turned into something so big. So that's really great to see the creativity. Okay. Yeah, so I really like that there's a lot of platforms and people are pushing ahead because we learn from each other. And frankly, we'll just have to see, you know, who can overcome the problems. The thing that's really good about superconductors is, you know, they work, people build systems, the errors are coming down to an acceptable level, and they're really fast. And if you like compare them to neutral atoms or ion traps, where they kind of have hundreds microsecond move times, they're many thousand times slower. And superconducting cubes, you need the speed, okay? And so that's why I think I feel good. The one thing that worries me is cost, because as you see, we're brute forcing it, and that's what we're trying to do, is figure out how to do cost, but also I would say do the reliability. So when we make a 20,000 qubit chip, okay, you know, we have to test that, and it's complicated to test it. So what we're trying to do is make that so reliably that, you know, of course you have to test it, but you're pretty sure it's going to come out. It's going to be cost effective. And you can only do that with reliable fabrication. So if you can make, you know, billions of transistors with a, you know, good process, we should be able to make 20,000. on, again, a good process. But we're going to have to get really serious about the process. So that's kind of the thinking I have.
Okay, thank you.
I think we're going back. Charlie, that's your job.
First and foremost, thank you for coming. And Professor Marcus, thank you for organizing the lunch for the student body. So really appreciate that. So during the lunch, one of the key points that you imparted was system engineering mindset. So I was hoping, I saved this question for a larger student body. So what would be the thinking mental model that students from different majors can ask each other to avoid subsystem optimization or hyper.
So this is for being in a quantum industry?
Yes.
Or,
yeah.
Okay. In the quantum industry, we need engineering expertise from a wide variety of people. Computer scientists, fabrication engineers, material scientists, list goes on and on. And we hire in this way. We can train you to understand about quantum physics, but generally, I think if you take one or two quantum physics courses on quantum computing, or there's a master's program at University of Wisconsin where they learn about that, that really helps us. Because that way, if you join our group with your specialized expertise, you then can understand what we're doing globally and contribute that way, because you have to have that mix of talents. For physicists, we like to hire physicists who know and like to build things, okay, because we're doing that all the time, and getting systems to work. And that, we really look for people who have an experience in that. And I think that's true of any employer, if you're going to be an engineer, you have to be comfortable doing that. Okay?
Hi, Professor. Thank you for giving that excellent lecture. So basically, my questions kind of follows the previous student that has been talking in front of me. So basically, my question is, could you explain more about how did your discovery linked to the semiconductor fabrication, and how is your? Could you explain more about how is your theory kind of sustains and make the quantum computing machine learning to be more sustainable, to be more reliable?
I didn't quite understand.
More reliable. For example.
Okay.
Yes.
Yeah, so there's two issues there. One is that the qubit errors have to become lower, okay? And people are working on something called the coherence time to work on the materials and interfaces and the like. When we look at this, we think the big issue is something called two-level states, which are occurring at the insulators on top of all the metals. The metals naturally oxidize. And these two-level states give us a lot of dissipation. But what's even worse is a two-level state frequency can overlap exactly where your qubit is, and then it kind of ruins the qubit and makes it much harder to calibrate. You can kind of get around that. So in our new fabrication method, we are working to reduce that by about a factor of 10 or 100 through the particular geometry we're doing that. So we think there's a lot of work that has to be done with materials and fabrication, and we're doing that. The other thing has to do with reliability, and again, by going to the semiconductor manufacturing, we think we can bring that up. For example, people make tunnel junction memories with billions of bits, and they yield it. 20,000 should not be hard if we build it properly. So that's kind of what we're working on right now to do that. We think it exists. You have to modify the processes. It's a lot of work you have to do. But we think it's just possible to do this.
Okay, thank you. Just to make sure I fully understand what you're talking about. So you mean what you're doing helps to eliminate the steps for doing with the semiconductor fabrication, which helps with combining multiple transistors to be more possible for doing that.
Yes.
Okay. Yeah, good, thank you, thank you. I trust you, I trust you. I don't know what I had just agreed to, but it's okay.
Hello, Professor.
We're going back and
Thanks
forth.
for the wonderful talk. And you were talking about scaling it to a quantum computer that's capable of having like 1 million qubits, right? So I want to understand how the algorithms scale. Like how difficult would it be if we have 1 million qubits processing information and we using algorithms to infer what the quantum computer just did?
So I didn't quite get, I have bad hearing, the acoustics bad. You're wondering in detail how we're going to scale.
Yes, it's
Okay.
like how a simple calculation can scale as we increase the qubits.
Yeah,
How?
so-
Yes.
Yeah, so the information is in that paper, okay? So I'm giving you the big overview here to motivate people to read the paper. Now, in the paper, I'm not going to give you all the good stuff because, you know, people will steal it, the ideas. But we've done the calculations. It's mostly the power consumption, you know, at the various stages. And the dilution refrigerator doesn't have much power, but neither is the signals aren't very powerful. And then you have to worry about the area. And when we go through that, it looks reasonable. You know, we have to engineer everything right. But, you know, the numbers look okay. So, you know, I've been doing this for a very long time. I know about low temperature physics. I'm good at thinking about all the problems. So I think we've thought about them and we can get by it. But, you know, there's things that we didn't think about and we'll have to solve that. But it just, when I look at it, I really believe we can build it, okay, from what I know how to do in my experience. I've done this, I've done enough crazy ideas over my career to know when, you know, it's way far out there or when, you know. So this is hard, but I really think we can do it. You know, and again, read the paper.
Okay, thank you.
And if you have more questions after the paper, yeah, we can talk. Maybe we want to hire you. Yeah, I know.
Hopefully I understand. Thank you.
Hi. So as someone who works with like silicon-based materials in order to like make something for a quantum application, I was wondering if you think that the semiconductor industry would need to change their fabrication in order to change to other substrates other than silicon, or we should continue down a silicon road.
Yeah. So I don't believe you can get 12 inches in other substrates. And, you know, sapphire is an obvious one. That you can get an 8-inch. And we're trying, but we're also trying to make this so it can fit into a existing line. Otherwise, you have to spend $5 billion to build the line. And, you know, I don't think people are going to do that. So we're trying to make it consistent with that. It turns out that you can make the qubits in silicon from all we see. It's just that silicon is soft enough that you get diffusion and all these effects that we have to work through. Again, if we're building this in a semiconductor fab, they know how to, you know, deal with the contamination issues much better than we do. So that's kind of the way we're thinking about it. Yeah, we just want to make it as standard as possible. Standard tools. All our tools are things that they already exist, and, you know, and they just have to put together the chambers in the right way, you know, to do everything we want. Yeah, so, you know, we're trying to do that as much as possible. But, you know, that is a constraint, and, you know, if we find that, we don't do it. But, you know, fortunately, silicon qubits seem to be pretty good.
Okay.
Yeah.
Cool. Thank you so much.
Let me say one thing before we go to the next question. First, thank you, and we're going to maybe stop the questions at the lines that exist right now. Otherwise,
But this can go on for hours, and I'm okay with that, but, you know,
I'll buy you a
that's
beer
fine.
later.
Yeah. It's fine.
So I had the privilege of starting my quantum career at UCSB in 2013. Never got to meet you, unfortunately. But now that I've got you in front of me, I've had this fantastical idea in my head for a while. that I loved your analogy of quantum computers today versus, or your PhD experiment versus computers in the 60s. I'm a little bit more pessimistic. I think we're still building paper tape and mercury valve machines like Alan Turing.
I think we're around 1960, not 1950.
Well,
yeah, but there was paper tape around then. Okay.
So really, the thing that I keep looking for in the signal is, when are we going to be able to find something where we move from a mechanical controlling an electrical to a electrical controlling an electrical, the same way that we saw with transistors and the density of scaling. So in that same analogy, moving from an electrical control system with a lot of classical computation, moving to a quantum control system of some kind, and what that might potentially look like.
Well, so what does that do beyond what I showed you, for example?
I think mainly the instruction flow stops being classical.
Oh yeah, people have talked about that. That is so far beyond what I can imagine. Yeah, I'm a very practical person, and I've heard about this, but I'm a what's they call him Peter Thiel 0 to 1, a definite optimist and not an indefinite optimist. So what I try to do is have a definite plan, which I'm showing you here in a lot of details, and then if new things come up, then we can pivot to that, and that's great. But yeah, unfortunately, that looks so hard. But I know in 100 years, maybe someone will figure out how to do that. But this looks very hard. What's hard is that the quantum part is analog control. And then that's pretty sophisticated and hard and has to be calibrated. And if that went to some kind of quantum, I just can't even imagine how hard that would be. So
I can't either. This is...
Yeah, okay, thank you. Yeah, thank you.
Thank you.
I'm an engineer, so I look at everything practically as well. And when I look at the consortium, I realize that it's basically US based. What's going on in China right now about this? Because my fear is that it's going to be competitive to everyone's disadvantage as opposed to collaborative to everyone's advantage.
Okay. So the effort in China is very significant. And when I read their papers, they totally know what they're doing. So, and they're very competitive with what, let's say, I know what Google's doing, I pay attention to that. They're very competitive what Google is. And the scary thing happened this December where Google published their latest thing. And then a month or two later, China published kind of matching that. And, there's a common way that people deal with this international competition is not to publish anything until someone else publishes it and says you're due thing. So it's possible that they're ahead. Now, what's really hard for me is, I want to be ahead, I'm doing it. I have a small startup company, and it's really hard to raise money from the government. And the government's worried about, I'm sure they're worried about this, but it's like, well, you could help us out. And it's like, we're trying to do something that uses United States superpowers to, fabricate this, actually that China doesn't have. So I just don't understand, what's going on. The only thing I do know is that the US government now is worried about so many other defense technologies that, they're probably, it's a high priority, but it's not the highest priority. You know what I mean. So, but yes, thank you. Okay, over here.
Hey, Professor Martinez, thank you for the talk.
Sorry, closer
okay.
to
So from my layperson understanding, one of the big reasons why we don't see any groups other than Cerebrus doing wafer scale integration is severe difficulties with yield. And I can only imagine that gets exacerbated when you want to do quantum error correction, particularly large-scale entanglement, when you might actually have end up having non-connected components because of yield difficulties. So how are you planning to cope with that problem?
Sure. Okay. So yes, and that's a very good thing. In terms of Cerebrus, I totally agree. They have many, many billion transistors. I don't know if people know that. Do you know that in the semiconductor, TSMC can yield chips up to about a millimeter around the edge of the chip? They're that good with yield control. And that when you talk to them about what are the yields are, like they have one defect or two defects on the best wafers. Okay, this is incredible. I feel if you can do that with semiconductors with, I don't know how many billions, many billion, trillion transistors, I don't know what it is, that we can certainly make 20,000 junctions if we get the processing right. And that might take some time. So I feel that that's, a pretty good indication that we can do it if we have the money and work hard at it. Now, what's interesting right now is if you look at the roadmaps of the other superconducting companies, they're going to make chiplets that are maybe 30 qubits or 100 qubits and then tile it up. How are you going to check those chiplets? You're going to have to cool it down. And there's no wafer prober at 20 millikelvin. And knowing the physics of that, I don't think there ever will be. So I don't know how they're going to build their systems right now because I understand low temperature physics because I'm an old guy, and I just see no idea how they're going to do it. You can't build a wafer prober. So right now, my personal opinion is we have a problem with the chiplet technology that everyone's saying they're going to do, and I'm offering something that I think is going to be more reliable. But it does mean we have to, build it a new way, and that's what we're doing. And, so far, I think we can do it. We have to fix some things. We can do it.
Very eye-opening.
But, yeah, we're not trying to make, a billion qubits.
Yeah. Very eye-opening. Thank you very much.
Okay, thank you. I enjoyed the question. That's good.
Thank you for the talk. I'm from an engineering background, wanted your perspective on how you see the scaling of the readout and control electronics, and what temperature, if any, you would keep them at, and how would they scale?
So the readout I don't talk about to the general audience. Right now, you use circulators and tupas that are this big. So what we have is we have an integrated circuit version of that, where we already have a paper by Robert McDermott showing that it works. So we integrate it on the qubit chip, and then we need an amplifier at 3 Kelvin. It's a superconducting amplifier with 10 microwatts of power instead of 10 milliwatts of power for the amps. So when we look at that system, the numbers look good. I'm not saying it's easy, but we think it's possible to do all that.
Right. Would it scale to the 20,000?
Yeah. You can. The integrated circuit is a small fraction of the qubit area. Okay. So and I think that's in our paper. Okay. So you can look up the private papers and get an estimate of whether you think that works. But that looks good. People are thinking about other things to do that, but I think we're doing something way simpler on the readout.
Thank you for the talk, Professor. I've got a narrow and technical question, which is, on these wafers, what sort of qubit structure are you thinking, like fluxonium, transmon, and is that something you're able to share, or is it just in the paper that I...
Yeah, so our default is the flux-tunable transmon and flux-tunable couplers, like we did at UCSB and Google. This was developed at UCSB, not patented. Other people have done it too, so we can do that. Well, I think that's good. However, if someone comes up with a better architecture, we're going to have the qubit fab, and we'll be able to make qubits for them too. So this is, I just want to build a quantum computer, and we can do that. So we're trying to build, the PDK and the things so that other people can build it also. And, I think we can do that.
And I guess what would be your advice to me and probably a lot of other students in the room who are interested into going into quantum engineering for the future? What would be your general advice?
It's a very interesting field. There are a lot of things going on. What I liked about the field is you learn very good engineering and very good physics. So no matter what you do in your career, that's going to be interesting. As I mentioned before, we hire a lot of engineers. Knowing something about quantum is really great. If you're a quantum physicist, we look to see if you have some engineering skills too, because we're building it. And we're very much in the companies in an era where we're building these big systems. And of course, we're also building it in really big teams. So you want to have to, work in a big team. And there's pros and cons to that, of course. We try to have a special culture in our company so that, you get to see what's going on. And it's enjoyable to contribute to the team.
Thank you.
Hi. You spoke at some length to the benefit of tapping into silicon manufacturing and semiconductor manufacturing regarding the pre-existing fabrication structure already being up to scale. With recent developments, artificial intelligence, data centers, blah, 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 all of that has basically had the orders to all these companies be placed as all of it and all of it as long as you can make it. As a smaller startup, working with companies like TSMC and similar, are you facing challenges being able to work with and find partners to continue your manufacturing?
Yeah, and I would say the biggest challenge is all these good companies are so busy making money off, AI that, they need to focus on that. But if you find the right company, they want to think about what's happening after AI, and then they're willing to talk to you. So, you have to talk to a lot of companies and see who's, really wants to step up and do that. But we've been able to find good companies. And what I would say is if they get interested and you convince the managers, they have so much expertise that can help us. And, we know about the qubits. We know how to design it. They know how to fab. It's a really good collaboration, And, it's always collaboration is hard, but we really think that's the right model.
And then quick follow-up then, you've mentioned TSMC a couple times. Does that make them one such partner, or is that just the household name?
Is TSMC a real partner, or was that just a generic name for those guys?
So we have talked to TSMC, and they've shown a little bit of interest for, one particular part of it. I don't think they're necessary right now. I think other partners would be better. They're just too busy doing what they're doing. Let me just say, talking to the TSMC engineers is an amazing experience. They really understand what they do. They're very precise. They understand what yield means. It was just an eye-opening experience, and I know why they're so successful. Just having a meet and greet conversation with them. I don't think they're necessary in the end because we don't have to do EUV lithography and do all these things. But, if we could get them interested, that definitely would be good for us. We find, however, that applied materials is good because they build tools and build processes, which is more what we're trying to do in figuring out how to put together our system. So that has been a very good collaboration working with them because, and then they, you build something that goes wrong and they go back and they talk to the engineer who's on that step, and then they'll tell you what to do or what they have to do and the like. So that's really, and I would say as a physicist, it's really fun to understand how the people think and understand their depth of knowledge on how to make these things.
Awesome. Thank you.
Okay, we're getting getting close to the end.
We are. Hi. Well, I wanted to thank you for coming out here and for a lovely talk and all of your expansive work in this field. I'm about to enter my career. I just defended my thesis about a month ago, or almost a month ago, and I'm looking at careers sort of in quantum engineering. I worked in like superconducting 2D materials and stuff like that.
Yeah.
And so this is sort of a very natural next step, looking into like superconducting qubit systems and stuff like that. But as I'm sort of considering these career options, I want to make sure that I'm like doing something that, you know, fulfills a grand, good vision for sort of where I want the world to go one day.
Right.
And I know you talked, somebody asked a question earlier about applications, and you talked about applications in like quantum chemistry and stuff like that. But do you have any concerns about some of the other possible applications of like once we do make a functioning quantum computer, like the powerful things that it can be able to do?
Well, you know, like I mentioned, I'm really afraid for Bitcoin. I don't own any Bitcoin.
Sure.
But if you look at the numbers, so what I do in my, ability right now is if I see that there's an issue, something to worry about, I talk about it publicly. So I tend to mention this. The Bitcoin is more of an immediate because it's an easier. I think that for the internet security, there's already existing solutions that are kind of out there, and that's going to be fine. People just have to switch over. But, you know, when I see something, I try to talk about it. And again, there are experts who really understand this in detail. You can go to their papers, but part of my job is to warn people. And, you know, that community really has to decide what they're going to do, because there's a real possibility there with, quantum computers doing something. So, you know, that's all I can do.
Understood. Thank you.
One last question. Okay.
Thank you, Doctor. And this is a really amazing talk today. And many people before me had asked many questions I want to ask. So my question to end this talk is, I want to know your research philosophy and how you choose a problem to solve and what pushes you towards the solution. And is there any advice for us?
So this is a really good question, because you're starting out in your career and what choices do you make and whatever. I can tell you with me, I went to Berkeley. John Clark was my teacher in the solid-state physics class, and I asked him about his research, and he was looking at quantum noise in superconducting devices. And, you know, quantum mechanics is mysterious and great. I love doing electronics. It was a very natural subject for me to work on. So I worked with him and, you know, was getting experience with him. I went to a conference and heard about this quantum, macroscopic quantum tunneling. There were some experiments, but it was clear to me that they weren't very well done yet. It's kind of all murky. So I went to my advisor and said, I think we should do something here. And, we talked about it, and then he figured out what we needed to do. So in this case, it was just, I had some interest, and I just, followed it and made sure that it would happen. This is, very much, how you should approach things. So what happens is you have to do a career, there's money, you have to figure out all this stuff. But you should always be on the lookout from some new ideas, some maybe new crazy idea that no one's doing something, but maybe you have an idea. You have to be very careful to look at it to make sure it's not a crazy idea and it's a good idea, because you can't waste your time on bad ideas, right? And then, you just try to do something that's very transformative. You look for those opportunities. And what I would say is, now that I'm meeting other Nobel Prize winners, basically everyone's doing things that's kind of transformative to their field that other people didn't think about, or people didn't think it was a good idea, or whatever. And, you just kind of have to think differently than other people. But, most of the time we're just worried about getting a job. I've always worried about that. And you have to balance all that, obviously. So, but this is hard. There's no magic. How do you describe to someone how to be creative? Okay, this is, this is hard.
How do I describe creative?
Yeah, how would you explain to someone, just be creative? Okay, that's a vacuous statement, right? But I told you kind of the way I thought about things. And I've done new things throughout the career. And in fact, I give the example of what we're doing at the end. It's different than everyone else is doing. I gave you the reasons why we're doing it. It's very hard. I think people think we're going to fail. And, there's some good reasons too. They're reasonable readings. But what I like about it is if we succeed, we will completely change how people do things. And that to me is, that opportunity doesn't happen very often. Okay. But I thought about this for years. Okay, there's a lot of stuff here. Okay?
Thank you very much.
Thank you.